Hi, this is Dr. Neff, and today I'm going to talk about solid-state structures and how we describe them. We're going to focus on crystalline solids, and shown here are some pictures of some mineral examples of crystalline solids, including fluorite, which is the purple one, copper sulfate, which is the blue one, rock salt, which is this one over here, and then beryl, which is aquamarine, which is the bluish one. Solid-state structures are really important to understand, as there's a big connection between structure and function, and whether you're an engineer or a host of other majors, you're going to learn about that connection between structure and function as you move on into upper division classes. We're going to spend most of our time talking about crystalline solids, as I said, and this slide here shows some examples of crystalline solids that exhibit all three types of the bonding that we'll talk about this week: ionic, covalent, and metallic. And specifically, a crystalline solid is a solid in which the atoms are packed into an ordered array. And there's a regular repeating pattern to that packing of the atoms that extends out to all three dimensions and goes out to infinity. It can be a little daunting to look at such a structure that big, so we've developed some ways to talk about it more simply, and one of those ways is a unit cell, which is the smallest repeating unit of the crystal lattice. And a unit cell must repeat in all three dimensions and give you the overall stoichiometry of that compound. And we'll look at examples of what I mean by that. We're going to focus on cubic unit cells, where the basis of the packing is a simple cube. And the first type of this type of crystal structure that we'll look at are simple cubic structures, which have the atoms on each of the 8 corners of a cube, and that's shown here. So you can see that this does go out in all three directions. And what I mean by that is, here's one unit cell that's defined by the cubic lattice. But you can see that that structure continues out in this direction if I drew in the atoms. So it goes out in that direction. It comes out in this direction if I drew in those atoms here and here. And it goes further out in that direction as well. And the crystal lattice is an imaginary boundary that connects the center of the atoms, as shown here. And so how much atomic material is in that unit cell is defined by that crystal lattice. And so if we shave away the excess atomic material outside that lattice, we can see that there's just one net atom within this unit cell, because there's 8 atoms on the corners that each contribute an 1/8 of their volume, because they're in 8 unit cells. So that gives me one net atom. And this picture shows how each atom is in 8 different unit cells. And this picture also shows the coordination number. If I focus in on this atom, you can see that he's touching a total of 6 atoms in the extended structure. That one, that one, that one, that one, that one, and that one. So the coordination number is how many atoms a single atom is touching in the overall extending structure. And this is one representation of how efficient the packing it is, or how efficient the packing is in a structure. And simple cubic is very inefficient. There's only 52% packing efficiency. And so there's only one element that naturally packs this way, and that's polonium. This type of cubic unit cell is a body-centered cubic cell, shown here. And this has, again, the 8 atoms on the corners. But now we have one atom in the center. So you can see now that there's 2 net atoms, because there's the one that's in the body center and the 8 on the corners that contribute an 1/8. So that gives us the 2 net atoms per unit cell. This is more efficient packing. It's up to 68%, and there's a lot of elements that pack in this way. The third type of cubic structure is a face-centered cubic. And as the name implies, now we have one atom on each of 6 faces, plus the 8 corner atoms. So now those 8 corner atoms give us 1 atom, but then the faces, a face contributes a half to the unit cell. So we have 6 faces times a half for a net of 3 atoms, plus the corner atoms gives us 4 net atoms for a face-centered cubic unit cell. And this is even more efficient packing. It's up to 74%, I believe. All of these structures that I've shown you so far, the simple cubic, body-centered cubic, and face-centered cubic, in order to be considered one of those structures, all the atoms have to be identical. But our ionic crystals also adapt these types of unit cell structures, although we describe them slightly differently, because now you have one of the ions packing into one of those basic unit cell types, and the other ions are filling in the holes. And so that's illustrated here for sodium chloride. And this is typical of ionic crystals, in which it's the larger ions, the anions, that take the basic structure, and then the cations fill in the holes. So if we isolate a unit cell here, you can see how this fits that pattern. So this will be my unit cell. And you can see that that's a face-centered cubic arrangement of the chlorides with the sodium ions in the holes. But it turns out that it's also could be described as a face-centered cubic arrangement of the sodiums with the chlorides in the holes. So it all just depends on your perspective. And so really what it is 2 offset face-centered cubic structures of the ions. So to go back to that structure, the first unit cell I show is looking at it with respect to the chlorides, but I could just as easily look at it with respect to the sodium ions, and you can see that that's also a face-centered cubic arrangement of sodium. So lastly, I want to show you how we can use the unit cell type to determine the empirical formula for an ionic compound. And this is just all using the different net number of atoms that you have of the different ions and putting those together in the smallest repeatable pattern to make up the empirical formula. So in this first example, I've got what we'll call it just a simple cube of, that's kind of a cream colored atom. With 2 purples in the body center. So that simple cubic of the cream atoms gives us one of those. And the 2 body-centered purples gives me 2 of those. So if I make my formula, which is kind of weird, cream to purple, there's 1 cream, 2 purple. So I could say that's CP2 if I'm just abbreviating. Let me move this other one down here lower. This other example is a well-known mineral. This is fluorite, which is calcium fluoride. And based on the positions of the atoms on the periodic table, the calcium would be a +2 ion and the fluoride would be a -1 ion. So the ratio that those 2 ions should come together in is a 1:2 ratio. So knowing that and then looking at the structure, we can figure out which of the ions shown corresponds to which element. So I hope you can see that in this structure we have a face-centered cubic of the white atoms, and there's an entire cube of the yellow on the inside. So that face-centered cubic of the white atoms gives us 4 net atoms, and the cube of the yellow on the inside, since it's an entire cube, it gives us 8 net atoms. That reduces down to a 1:2 ratio. And so the white must be the calcium, and the yellow must be the fluoride, because then that gives us the correct ratio that we want of 1 calcium to 2 fluoride ions. Let's do a couple more examples. This is sodium chloride, which we have already looked at before, but this shows it from the perspective of the smaller ions. So the purples are the sodiums. So we have a face-centered cubic of sodium ions, and so face-centered cubic is 4 net atoms, so we have 4 net sodiums. And then if you look at the lattice structure, the chlorides in that lattice structure are on edges of the cube, and those contribute 1/4 of their volume. So I've got 12 edges times 1/4. No, I've got 12 edges. I've got 12 edges times 1/4, so there's 3 net chlorides there, and then you can't really see it, but there's 1 chloride in the body center. So that gives us 4 net chlorides also. So I've got 4 sodiums to 4 chlorides, which reduces down to a 1:1 ratio and gives us the formula NaCl that we would expect from the periodic table, because sodium is a +1 and chloride is a -1. So they should come together in a 1:1 ratio. And the structure shows that. Okay, so the last structure I want to show you is this one right here, and this is called a perovskite structure. This is a very common unit cell type for a lot of different minerals, including calcium titanate, which has calcium, titanium, and oxygen. And so this shows, let's see, this shows the calciums on the corners, the titanium in the body center, and the oxygen on the faces. So that's going to help us figure out the correct formula. So looking at those calciums, the calcium being on the corners, that's 8 times 1/8 to give me 1 net calcium, and that's a +2 ion. Looking at the oxygens on the faces, there's 6 of those, each contributing a half, so there's 3 net oxygens, and that's a -2 charge. And then my titanium is the one that's kind of hard to see, but it's there in the very center. So that's 1 of those, and it contributes its entire volume to give me 1 net titanium. And titanium is a transition metal, so it can have multiple charges when it forms an ion. So we're going to use the resulting formula we just figured out to figure out the charge on the titanium. So we have 1 calcium, 1 titanium, and 3 oxygens, so that would be my formula. So from the oxygens, I know that I have 3 oxygens, each at a -2, so that gives me a total of -6 from the anions. So my cations have to give me a +6 to balance that, because it's a neutral compound. So calcium is +2, so +6 minus that 2 leaves me with a +4 for the titanium. So again, we have a -2 for the oxygens, a +4 for the calcium, or +4 for the titanium, and a +2 for the calcium, and that all balances out. The thing I want to leave you with is this structure, which is another very common mineral structure, and that's called the zinc blende structure. Zinc blende is just a generic mineral name, but it corresponds to zinc sulfide. So you should be able to figure out what the formula is for that based on their positions on the periodic table. But this also, like I said, it's a really common structure. So this one that I'm showing here is actually for boron arsenide. So your goal is to figure out what the formula for that is, and so give it a try, and thanks for watching.